Thank you. Okay, this is about a work that I, myself, an Atlas member, have been doing together with my two colleagues, Dr. Sekman and Dr. Prosper from CMS. The idea is to talk about the future of the analysis description languages. As you know, so far, the analysis that we have been doing in LHC experiments are mostly done with the general purpose languages like C++ and Python. And when I talk about an analysis, I usually refer to the analysis for the whole ecosystem, which contains event processing, histogramming, input data type management, workflow management, and even including the statistical analysis tools. Some of us were thinking, what should be the future of this endeavor? And we thought of moving in the direction of analysis description languages for the high-energy physics analysis. We want to create this language, which would be domain-specific, meaning it will be specific to this particular task of high-energy physics analysis. It will be an embedded DSL, meaning that the syntax will be similar to a general purpose language. We wanted to create a declarative language. That means the language will be describing what needs to be done without referring to how it is going to be done. And most importantly, it should be human readable. An analysis description language, as it stands, should consist of, we said, a plain text file that simply describes the analysis with very clear syntax rules, and a library that will contain the functions, encapsulating necessary variables, functions, etc. Of course, this library is supposed to have a number of internal functions, but whatever is missing can be added as external user functions. This effort has been discussed widely in LHC, and we created something like LHC Analysis Description Accord, which was published in this workgroup report in 2015. And in parallel to that, I have been working independently on a similar syntax with slight variation, which was published in this reference at the bottom. The name of the language at that time was called Kotlang. This analysis description language concept, we believe, will be useful for both experiment phenomenologists and public enthusiasts for a number of reasons. First of all, it will be helping preserving the analysis because it will simply describe what needs to be done. Of course, the analysis design and its implementation will be simplified as well. That also helps with the communication of the analysis, communicating the ideas, communication of the algorithms, and visualization of the algorithms. When it comes to the refereeing the task, I think it will be helping with that as well. Of course, another extension would be interpretation studies, re-implementation studies, and at the end, comparison within the experiment and between experiments. We started with this idea, and let me tell you what has happened since then. Currently, the LADA concept and the Kotlang concept has been unified under this name, ADL. We have this web page at CERN, which describes the current situation together with some important links. We have published the syntax rules. We have an implementation, which is based on root. It contains mathematical, logical, and some high-energy physics specific functions. In this tool, it is now possible to define variables, new objects, user functions, histograms, tables, efficiencies, reducers, optimizers, that kind of thing. The syntax is rather simple. I have included in the yellow box on the right-hand side. The syntax looks like keyword value structure, separated into blocks, defining objects, running algorithms calling other algorithms, etc. The whole setup currently has two implementations. One is an interpreter and the other one is a transpiler. The interpreter also contains a framework which is capable of reading multiple input data types, such as open data, nano AOD from CMS, Delphis, Atlas, etc. It has been recently used in one Atlas exotics analysis and another one, another phenomenology analysis for FCC. The transpiler itself is also available in this web address that I gave you. And we have a number of analyses, about 15, implemented in ADL, which can be found under the GitHub link that I gave at the very bottom of the page. My last slide is about where we are going. Now, these tools, the concept and the tools are actively being developed. There are two FSU and UCI universities involved from US. There is Korean and Turkish involvement. And also CERN has supported our project via a number of summer students. We hope to implement more analysis for the database. The interpreter is using modern tools like Lex and Yak, therefore it's ready to be publicly tested. We are, of course, planning for more work on this, and the emphasis should be implementing systematic error evaluation and an integration of a statistical analysis tool. Thank you.
Thank you very much, Gokhan. So we have one hand up already. So Andy, do you want to go ahead and ask your question?
Yes. I have a question. Why did you choose or was there a reason not to take any, let's say, given language format for storing the syntax, something like a JSON format or something where already a lot of industry tools are there to read it back in? What was the incentive to come up with a text it looks like text format, right?
Indeed, it is text format, and yeah. The nice thing about text format is you can actually read it as if you are reading a simple English text file. For editing with JSON, of course, there are tools that you mentioned. However, you have to use those tools instead of opening the analysis file in a simple text editor, Pico, if you like.
Yeah, I would come from the other perspective. For a long time, I think we have risk in HEP almost too much that we came up with our own solutions and were disregarding industry standards. So this is something where I think we also, and I think this is, since it's an HSF workshop, I want to say it also from that perspective. We also have some sort of an educational, let's say, aspect within the HEP Software Foundation, from my point of view, that young colleagues working with us, when they leave the field, ideally should have worked in an environment which uses common tools. And I'm not saying but this particular example, but I think given the past, we have been very often prone to come up with our own solutions for something which probably could have been like solved in a more industry standard way.
Look, I can take your comment and run with it, just to say that the C++ is industry standard and we should continue with it. I think each problem requires its own perfect tool, ideally, to solve it. And I believe, especially for newcomers, as you mentioned, having a simple text file without any extras is much simpler to work with. Given that, there are tools, obviously, that can convert from JSON to text to JSON back, and Root, which we are based on, contains some of these tools. In a sense, if you want to insert another layer between the analysis description language itself and the person editing it, well, you can do it, of course. It comes for free.
Thanks. I think let's move on to Attila's question, just because we're running out a bit of time for the discussion.
So mine is not fundamentally different either. I was just wondering, along the same lines as what Andy was asking, that how much of the current development was spent on writing the just the text parser and tokenizer and all of this, because I myself could very much see an interesting development in writing a specific analysis language, let's say on top of LLVM, where we would introduce some nice like analysis focused language, like how Apple introduced Swift, and then compile that down into some code. That I would find sort of interesting. If this is mostly just automating some relatively simple things, yeah, there I see a little bit less of a revolution with this.
Now, first of all, let me admit by saying that I don't know much about Apple's Swift, but I can tell you what we have done in this tool. The parsing is done through Lex and Yak, so this is pretty much automatic. And it is building, the interpreter is building a function pointer tree, which is getting evaluated at runtime. Does that answer the question?
It does sound competent, at least, that you use those tools for the text parsing.
Yeah, right now what we have is a prototype. Eventually, we are planning to get involved, a real computer scientist, not the computer scientists wannabe physicists like ourselves, and implement a proper version of this tool based on the intermediate representations and LLVM, as you mentioned. But currently, what we have, although it is at least in a workable state, is basically a working prototype. An advanced prototype, maybe a beta version if you want, but still something implemented by myself plus, physicists.
And just to jump on this, so at that point, and maybe I just didn't understand fully what you were saying, but at that point, would you foresee that in this language you would actually be able to write like fundamentally new code, like in any generic language? What I mean is that to be able to express types of analyses that were not foreseen before.
Gokhan, try and make it a quick answer because we're running a little bit late. Remember, folks, we have the workshop notebook to carry on the discussion.
Sure.
Okay. Since we have a number of logical and mathematical operators, any function that can be expressed in terms of existing internal functions can be written. Transverse mass of W, of course. But if you have a complex function, something that is the result of a machine learning algorithm, if you want, that can be added as an external user function, compiled once, executed at runtime.
Super. Thanks, Gokhan, and thanks for the interesting discussion, but we'd better move on.